Okay. I think we can get started. Just quickly announce.
So, bem-vindos a todos aqui no chat. Como esse curso vai ser em inglês, então vou passar para inglês. Aí vai começar. Então, welcome everyone. I see everyone in the audience. Welcome everybody online also. So this course, mini course, is part of our summer course here at the end of Star. And it's with my pleasure that with this David Cutkosky will talk about resolution of singularities. So it will be 3 courses. So all the 3 courses will be transmitted in the same link. So everybody who is here, feel free to join the other times. And everybody here. Okay, so.
Okay, thank you. If anyone has questions, feel free to stop me and ask. I suppose, I don't know, you can monitor your chat, I suppose, but I don't know that I always find this very difficult to try to keep track of that.
Yeah, but I will keep track. So if somebody has questions, you can just post here and yeah, we'll pass to the speaker.
Okay, great. Okay, also, I guess everybody, both people online and people here, should let me know if they cannot hear me or they cannot read what I've written or in general have other questions. Okay, so this is a course on resolution of singularities, where I hope to at least explain the basic ideas of this. And I guess it's from a book of mine, which was published a few years ago, that sadly there's not been tremendous progress since the time I wrote the book. So I think but I'm going to be talking about some of this, and I hope I'll be able to convey the basics of this. So what we're going to start out with is giving a quick introduction to the subjects of algebraic geometry and the commutative algebra as is relative to this. So some people may already know this, some people may not. I hope to present this in such a way that everybody will at least be able to follow the ideas of it. Okay, so the first thing is we need to know what a defined scheme is. So that is, you take R to be a ring, our commutative identity, and then you take a spectrum of R. This is going to be the set of all primes E contained in R, and you have a topology on this. Topology where the open and closed has VI, and this is going to be points and primes and spec of R, such that I is contained in P. So this is a so-called Zariski topology. It's not Hausdorff, but it works well in algebraic geometry. U is equal to spec of R. There's a sheaf of rings. I'll say a few words about what a sheaf is. You don't really need to know what a sheaf is. Then what it, which is the most of U. And basically what a sheaf is, it associates in any open set a module or a ring. It associates a ring in this case. And this is consistent under restriction. So the model for the sheaf is any reasonable class of functions on the ring. So that's the model where you have some restriction functions and you can have germs. So if you have a point P in the space, you can look at, well, essentially the functions on every neighborhood of this point, no matter how small the neighborhood. So for instance, in complex analysis, or like the case of you take on C, the analytic functions on C, that at any point, these terms are just going to be the analytic functions which have some radius of divergence at that point. It could be very, very small. Okay. So this is determined by the condition that this stock is equal to it's equal to R localized P, that localization for all P R. And one is said that this is equal to the element A over B, so that A is in R and B is in R. So you invert everything which is not in P. Okay, so and then so the basic fact that you need to know about this is OXU is equal to R. So if you think of these as functions, this is usually viewed as the regular functions on R, that this sheaf that the global sections, as they call it, it's just all of R itself. Those are the functions. Okay, so they also have, so now I think we don't even really need to worry about what a sheaf is after this. That also we have that the scheme X, we need to know what this is. This is a topological space with a sheaf of rings. The sheaf of rings divided on X, such that every point in X has an open neighborhood for a Q, such that if you restrict, so that U itself is a pi, and if I restrict x to U, this is equal to this OU, the way I defined it over here. So somehow you glue these things together, they have to be nice algebraic math somehow, but this is the basic idea. Okay. Now let me give an example which will hopefully motivate this a little more. That we're sort of about the middle of Hartshorn right now, so we're going fairly fast. If you haven't seen this before, Hartshorn is sort of the standard textbook on this, in algebraic geometry. But here's the idea. Drawing this can to be a field, and you take a polynomial, maybe several variables. Well, I think big enough, I think, is my sample.
I think so.
Okay, if it's too small, let me know.
Yeah.
Okay, then I is an idea. Okay, so then now we take R to be this function. Like that, and then we can identify then the set of R as a topological space. This is going to be the V of I contained in the specification by the formulas. So this is one of the basic theorems about rings. There's a one-to-one correspondence between the prime ideals of R and the prime ideals of this bigger ring which contain I. So that's exactly what this is. Okay, now this, I think what got this whole thing started was we have this really nice statement that K above very close. Then the maximal ideals. So this polynomial ring are exactly the ideals x1 and n for some elements a1 f a n in K. Okay, so somehow the maximal ideals that these really look like points. And of course, if you take an ideal like this, or well, you just take the quotient, you see you get back to K, so it has to be a maximal ideal. K is the field, in this case the field, and this is the theorem of Hilbert's. This is Hilbert's corollary to Hilbert's Millstone and Sons. Okay, so this gives an identification. Identification of a closed point. While we're dealing with that means of x spec of r with the actual physical points when we normally think of them. And here it is again. A1 and are actually in, well, I can go put it this way, that these guys will vanish. So that A1 are a is equal to 0. And then to express the generators of the ideal as that point down through that far. So it's a polynomial ring, every ideal is going to be generated, so you can always do. Okay, so this is something fairly geometric. Closed points means that you can take the closure of it, it's itself. Okay, but that most of the prime ideals, like for instance, you take the zero ideal in here, and you take V of 0, that's going to be every prime ideal in this ring. Okay, so it's not closed. The closure of the zero prime ideal is the whole spectrum. So, but if it's a closed point, if it's a maximal ideal, then there's nothing above it, okay, except for itself. So it's closed. Okay. So now let's talk a little bit about commuted algebra. The so-called full dimension. Ring R is the maximum of T such that P0 contains P1 contains PB is a chain of distinct branches. Okay, so it turns out that this gives us our usual notion of being, this gives our usual notion of dimension of the space as will indicate. In fact, we have, if we take a polynomial ring, it's equal to A of X colon N, we're going we call this an N, find N space, and the convention or so, and then it's equal to, I guess what I should have said is dimension of A, and this is going to be, in fact, more or less by definition, the total dimension of this, which is, so again, this is really a definition that the spectrum of something, the dimension of it is the dimension of the ring itself. And you can define that topologically also, purely topologically, the maximal length of the chain of distinct irreducible closed sets. And this is the theorem, which I believe this is in a T.M. McDonald, for instance. I think everything I'm doing with commutative algebra is in a T.M. McDonald 3D also. And this exercise, he explored a little bit about these concepts of like the spectrum of the ring and its sheaf of functions and so on. Okay, so now let's look at another example here. It's very important to algebraic geometry. So let's take an idea of R contained in this case, R is K, X0, X1. And this is a traditional construction equals 0, where this is a polynomial. And you can speak about homogeneous. So let's take this to be about the R homogeneous. So a homogeneous element is the sum of monomials of the same degree. Okay, so if we take a monomial, the degree is just the sum, so the monomial will be a power of this guy, times the power of that, times the power of that, you just add up all the powers. That's the degree of the monomial. And for a polynomial to be homogeneous, that means it's the sum of some elements in K times monomials all in the same degree. Okay, so there's a very important construction, which this is the product of the gradient ring. So the product of R and I, this is going to be the stack of homogeneous primary field. This is called the monomial ring. Which one we got to figure out? I want to assume that it's not this gradient maximum. That's certainly homogeneous, and you don't allow that one. So this may seem a little mysterious, but it allows you to construct the usual projective space. So this guy over here, this is a scheme. So the topology of this the closed sets. Closed sets are the sets B, A, and this is equal to B in the project for on J contained in E and for J homogeneous in With or without. Okay, so of course, you can take this bad one there, but then it's the empty set. There's nothing in it. Okay, so the important thing is that since this is the empty set, you've thrown away that prime. Then the power to the normal line as the open cover. Over here of use I. This I is equal to the prime of R I. And then I remove from this on V of X of I. Or okay, so the point is, what is the union of all these things? It's everything except for this guy. Okay,
So-
but
Just a comment from the audience. They say that I think in the definition of proj R moduli, you need to ask the piece to contain I.
I think they're absolutely in I. That's right. That you're absolutely right. Thank you. Okay. Yes. Thank you. Okay. Absolutely. Okay. So this we have this open cover, and because of this condition, and in fact that we have the fact that you are is in fact a filling. Okay. Here on xi, something over xi. This is a polynomial ring, and then you mod out by 1, and I should have said somewhere that I is equal to f1 and f r and by homogeneous. And then this is f1 of x0 over xr and so on xi. When fr that is not over xi f2 xi. Okay, so it's a nice simple formula, but in doing calculations, especially studying properties which go back and forth between when you dehomogenize and then you can homogenize to go back, they can get a little subtle. Okay, so basically, we like to define things better. We're just looking at brain script, but somehow you glue all these things together. And somehow the global properties don't really play a big role in resolution of singularities, like they do more so in other topics in algebraic geometry. Mostly the idea is that one wants to sort of reduce to looking at some nice affine ring or even some local ring, but you have to be kind of careful about this and rather than resolve it. You have to sort of consider everything. So I'll say more about that. Okay, so again, that's the example is equal to vector space over projective in space over K. So basically, this is the thing which is this can be interpreted, say if you're over the complex numbers K, so if you take the t to the n and you remove the origin, and then you look at all the lines from the origin, even though you remove the line that they would contain it, and you look at this as a set, and then you put a topology on that, and that's what this guy. Okay, so.
You said Cn, you meant Cn plus 1, right? The lines on Cn plus 1. Right?
Oh, yeah, you're right. It's Cn plus 1. You're right. Yeah, so you have to start with Cn plus 1. Go. Absolutely. Okay. So basically, the scheme X is called a variety. If X is connected, and OX, the local one, is a variety. And that's, it's a domain, sorry, it's a domain. Yes, okay, so this is the, if you have two different, components of that, so it basically says that this thing is irreducible. There's only really one irreducible component in the, three-speed topology. And the domain condition comes if you have two things crossing, then you pick a point where they cross. And then you cannot have a domain anymore. Okay, so okay, so that's subset of the N is in a flowing variety. It's equal to V of P, and O accepts. It's going to be taken to regular functions on AN, modulo of P, where P is a prime idea. In other words, this guy is a domain. And then I will make. So what is there is the analogs of predictive schemes and varieties, and I have to define that. Okay, so I'm going to it's equal to this construction. Modulo ideal. Is ideal. Then X is a projected variety. That's what the projected variety is. No, sorry, scheme. I meant to say scheme. Okay, so if it was the irreducible analog of this, then we say that X is a projected variety. Okay, so now let's talk a little bit more about commutative algebra. This is also in the theory concept, what I'm going to talk about, which is the concept of irregular local ranging. So now we're starting to actually approach the subject of resolution of singularities. Before we can resolve the singularity, we have to know what singularity is. So we will get to that, and we will see that what a singularity is much simpler in characteristic zero over a field like the complex numbers or even the rationals than it is over a field of characteristic E, or even worse over something like the integers. Okay, so we start this now that we've learned everything about geometry. Okay, so what's that R is a local ring. Okay, that means that we need maximal ideal. And the way it comes up in algebraic geometry is that if R is any ring
P, ideal. And then we the form that are localized at P, but that I described before. This is a local ring with maximal ideal. Localized at P. Okay, so it's just every element of P divided by things which are not in P. Okay, so this is, and we discussed this a little bit. Remember, these are the local rings of the sheet. Okay, so what this means is somehow you're throwing away everything. You're getting rid of all the total ideals which are not contained in P. Everything else becomes unit ideal. So you're really focusing attention on what happens very near this prime, and any bad behavior that the ring has, which is away from P, you lose it. It just disappears. So any good or bad behavior that this ring has is something which is a local property near P. Okay, so okay, so R, the local ring R, maybe I should have said A here, because I had that. Okay, like that. It's a different stage of Mars. Okay, so R, we know local, we the maximal like beauty, more like ideal. R. And one has this wonderful formula, which is the dimension of R. And I'll explain a little bit what dimension it means here. Okay, R like MR, the maximal R, MR squared. Okay, so what is this? This is connecting with the full dimension of R. Okay, and this over here is well, it's equal to a field. That's R is a maximal ideal. So this over here is a vector space dimension. That's pointing to this. And this would be R by M R vector space dimension. So they're really different types of dimension. Okay, and so and this will be finite for utilitarian local ring. Okay, so the critical condition is where things are really good is when you have equality. Okay, so when it says if equality holds, namely the dimension of R of R squared and R equality. Regular local dimension. Okay, now these rings have many good properties, and I'll abbreviate them like this. For one thing, regular local ring, and many good properties, but you won't go too much into, but one's very important, including This is a very powerful concept, being a unique factorization domain, which allows one to prove many nice theorems about schemes or varieties for every local ring is a regular local ring. Okay, so this actually is kind of interesting. This, at least for varieties over the complex numbers, or even complex analytic varieties, where the sheet is of the analytic functions, that it's been known for a while that localization of, the germs at a point, the germs of, power series which are convergent within some radius. That those are, that ring, well, first off, it's Noetherian and it forms it is in fact a regular local ring and it is a U of D. So this property being U of D, this was probably known by Garstrass even, and then also certainly the famous chess champion last year proved this also for this analytic case. And the final version of this was only finished relatively recently, in late 50s or early 60s by Balsander and Buxbaum using methods of the homological algebra, which at that time was a great new ideas at the beginning, wonderful theorems being about because of it. Okay, so there's one particular construction that I'm going to mention here about what regular parameters are. I'm not sure we really need it, so maybe I won't define it. But this condition is very strong. Let's look at this another definition. Suppose that X is a scheme over the field K. So let's say we can assume X is a quantity. Then we can write X is equal to the factor K of X1, Xn, the modulo sum of yield. Then like that. So in fact, since this is a local condition, we can always assume we're in this case. Okay. On the define the determinant matrix matrix J X is equal to J F1 to Fm F1 Fm in the familiar way. This is just the matrix del F1 del X1 del X1 del Xn, and you go through all of the variables. Hopefully this is readable. Okay, so it's an n by n. It's an n by n matrix. Okay, so let's suppose that so if I call this idea equals I, and here let's let R. When R is equal to the spec of sorry. Let's suppose that we take a point T and in X. We can R. Okay, so P. Let's see the one minute. So I think it's if we're borrowing something. Okay, so I think that is to become. Okay, so I should say probably, let's take this point here, N bar, and then, there exists, suppose N bar is an, spec of K of X over X, and N bar is the M, M bar is equal to M bar times bar. So, it might be the whole thing. I think I wanted to take this in here. Okay, so. Okay, so we have this condition where we take this maximal ideal in here, or our prime ideal containing I, and then we're looking at this. Okay, so let's K and bar with bar localizing and bar on is then ideal, which is a field, and this is equal to the quotient field of R bar. So if it's quotient,
I suppose the field should be contained in R, right? Because R is this quotient, right?
yeah, but it should be contained in R, that's right, yeah, it should be contained in R. That's right, it should be contained in R, absolutely. Okay, so there's a criterion, which you may have learned, in a linear algebra class, and then maybe not too, it's usually not in the standard engineering type books, which is that you can determine the rank of a matrix by looking at its minors, namely all of the square the determinants of square submatrices. Okay, and that's what we're going to use here. So we put it in as rank L at this point and bar is the image of the L dimensional generated from X, which is generated by the jump bar coming millimeters. Millimeters of X in this field K and bar is in fact all of K and bar. Okay, so that's this condition, and you need to talk about the image of the house sitting on the field isobas and X in K and bar. So it is 0 or less. So what this tells you is if you take this matrix here, which is a matrix of elements, in fact, in this ring, and if you reduce modulo by multiplying out by n bar, then you can get an invertible matrix. This, in fact, the rank, as you learn in linear algebra, is going to exactly be L of that matrix. Okay, then Okay, so that's the condition for rank. And now we can define what it means to be smooth. Okay, let's suppose that X is the variety of dimension S over P of K. And point and X. And let's suppose that U or respect to Y. Define neighborhood of P such that R is isomorphic to K of X1, X of Y, where R is equal to one onto background. That's one situation we've been discussing. And then I can now say what it means to be smooth. It's smooth. P over K in this matrix J and X and Y and minus S and P. So the first thing one should ask is that, well, there's a lot of choices involved in this. First off, I find a particular applied neighborhood, I represent it a particular way, and particular generators for the ideal. And this business about the rank of this is independent. But you get the same answer no matter what you choose. Okay. So maybe I should make that one. This definition. Solely. Okay, so I should make a comment that, well, this may look familiar, this construction, although it may look a little more complicated. But if K is equal to C, for instance, then the next smooth this implies a suitable projection of U onto C sub S is an analytic isomorphism. Yeah, good. Okay, so I guess this is the inverse function here. Okay, so, but the point is that this works in this very general situation where K is any field. Okay, so if everything works very well over complex numbers or other fields of characteristics 0, but if you have fields of characteristic P, then things get more complicated. Okay, the first general theorem, and let's be things are proven in most books like the algebraic geometry, at least for algebra or the fields. It was the reason that it works all this theory out into one arbitrary field, including understanding what the differences are in the characteristics. Is that no points? Okay. Variety. Which are smooth. Over K. And then subset of it. So in fact, this just follows from the fact that you're detecting smoothness by looking at the vanishing of whether points are contained in this ideals and fitting ideals or not. So that's a closed set. So that's how you get this. Okay, now here's the major theorem. Okay, so we'll say that suppose that X is a variety. And this criterion makes sense for closed points. X is a variety over a field A and X. Then the first statement is that suppose that X is smooth over K and P. Then so P is a non-singular point. Okay, so then
Say the non-singular is regular. What is the form of regular? So it's the same?
yeah, that means what this means is that OXP is a regular level ring. So if something's smooth over K, then this is regular. Okay, and now the second statement is that suppose that P is a non-singular point. Over X and K of P. So that's where you take OXP and you modify its maximum ideal. It's separately generated over K, or ground field. This will be contained in K. And you know that X is smooth over K, but that if you don't have this condition, it could be a non-singular point, but if K of P is not separately generated, then it won't be smooth. Okay, so in fact, really, this is this a necessary and sufficient condition for the point to be smooth over K is that these two conditions hold, that it's local ring, it's a regular local ring, and its residue field is separately generated over K. So
Can we just remind what separately?
I was about to do that.
Okay.
Okay, so in fact, this is a generalization of the notion of being separable that you learn about when you learn field theory, Galois theory, so for finite extensions. So field L is separable over K. And this I'll say something about what these things, so separating transcendence on basis of over again. So what does this mean? This means that always you have an extension argument. Well, okay, if you're in the world of algebraic geometry, you always have an extension, a situation like this, where this is a rational function field and variance. This always happens. So if it's a transcendence basis of L, then you'll have an inclusion here. What this means is it's a quotient field of a polynomial.
You mean at least separately generated, not separable, right? Otherwise you get a loop.
Let's see. No, I don't think so. Why is it? Why am I getting?
Because a separating transcendence basis is a basis, transcendence basis such that it's missing separable, as algebraic separable, right?
That's right, but I'm just saying that you call that separable instead of saying that. Instead of defining field, what did I write over here? Separately generated. I should have said separately generated.
Oh yeah, that's what I'm saying.
Yeah, you're right. I missed that. There's also the concept of being separable, or that's a
Yes.
sophisticated concept. And in many situations, it's the same. But
Yes.
Yeah, you're absolutely right. Yeah, I this is that. Okay. But this is the definition of separately generated, which is the one that's relevant for us. Okay, so what this means is, however, and separate. So finally, okay, so this is the situation one learns about for finite field extensions to be separable. Okay, so this is so in other words, yeah. So it's like that. Okay, so
I suppose you would say, but the theorem is saying that in characteristic zero, these two concepts of being roots and being non-singular are the same, right?
right, that's absolutely right. And that's the next
Okay.
next thing. But that's good to do instead. Okay, so before, in fact, I'll say something a little stronger. Is suppose that X is a quantity over a perfect field, and I'll remind you what that is. Perfect field K. And P is in X. Then like this, singular, and E, definitely has a, and it's smooth. Okay, so what is perfect mean? That is characteristic K equal to 0, and K is perfect. Always by definition, but if the characteristic of K is equal to P bigger than 0, then K is perfect. And for every not known of K, that has a P root in there. Okay, that's what it means. So it's a vacuous condition in characteristic 0, but it always holds. But it's a real condition here. So, for instance, all finite fields as sigma E, the sigma easy, which equals to right like this, characteristic P, all finite fields perfect. Okay, but a simple example here is one perfect. This is like take the rational function field. T, where rational function field. It's not perfect. In fact, this is the standard base field over which we can generally find some sort of bad example. I mean, the point is that the P derivative is not a rational function in T. Okay, so in fact, there's a lot of concern about this. In fact, as I mentioned, it's Zarinsky that we have this distinction between the regular points or and the non-support non-singular points and the smooth points. Okay, so what P is a prime and P is determinant. Determinate that's this guy up there. And then you take R to be K join plus Y, I, plus the P plus Y to the P minus P. And X equals step with R. This is the demand. Well, check that. Because you can't take it any further T. X is X equals to spec of R. And in fact, X is non-singular, but there are no points where it's smooth.
There's FP.
What?
F.
Oh, I guess,
There's notation,
I guess, yeah, it could be consistently with I don't, just being clever right now, we're introducing some new notation. I got them into trouble. Yeah, that should be consistent. Okay, so. Okay, now this is this one. X is non-singular. In fact, a non-singular variety. But there are no points no points on X which are smooth. Okay, so effectively what this means is that for this particular guy, the spec of R, you can't, it will not be possible to remove the singular. It's so incredibly singular that it's not possible to do so. However, if you take the definition of being non-singular to be smooth, but it's still, there's, well, this one's you're already done, in fact, if you're in, because it's regular everywhere, if you take this definition. Okay, so the proof, well, the first part is since I put a trick in here to make this look harder than what it really is, which I will undo. Okay, you know that R is isomorphic to K, which will UY, that's a polynomial ring. P is T. U is equal to X plus Y, making that substitution. And this is isomorphic to the 1 over P going Y. So this is a polynomial ring. over the field. Over P, and I think we observed that all polynomial rings over field are non-singular. It should say, or it's regular. X is equal to the bar, singular. Well, since all polynomial rings are regular. But you can check that explicitly, for instance, at the defining condition global. Over field are regular. So by this, I mean any prime we won't get localized that it'll be regular. Okay, now the next condition is to see why, so we see it's not singular. Now we need to show that all points, there are no smooth points. Okay, so let's verify that. How long am I supposed to go? Am I out of time?
No, absolutely.
No, I start at 4.
At 4, yeah.
So then it's 5:30, is that right?
You can go up to 5:30 or, before this.
Okay, okay, I'll get to a good stopping point, which is somewhere around that.
Right.
Okay, so certainly I want to show this. Okay. Okay, so we take the formula. And there that, and then we compute this K fx y, and this is the number one equation that yield derivative by delta y. And in fact, you see this is 0, 0, because if I take this guy over here, I take the derivative with respect to x, well, that's p times x to the p minus 1. But since for characteristic p is equal to 0. Okay, so it's 0. And the same thing over here. So for this, we infer that f(x, y) as rank 0 in p for all p in x. So we have S is equal to 1, which is equal to the dimension of the X. I mean, that's something you can check that this is a one-dimensional ring. And we also have n is equal to 2. There were 2 variables. And we have 1 is equal to n times S bigger than the rank. J F X Y is equal to 0 on always. Okay, so we're going to evaluate this at any point P that equals 0. So by our condition that remember being smooth, you have to have equality right here, and we never get it. Okay, so there are no smooth points on X. Okay, so in fact, this is, there's a big controversy over this between Cutkosky, who he had a really beautiful paper he wrote in the 40s, I think, which is describing on the concept of a simple point, simple non-singular. And he goes through a very sophisticated analysis of what happens over different fields, comparing with this classical smoothness condition. And he concluded that we're really forced to take this definition of non-singularity being regular. For instance, that you're throwing there's a lot of things that you just can't hope to resolve if you do this. The Andre Vail did not like this. He had a whole machinery built around the classical notion of smoothness, and to this day, most number theory still follows one great dial on this. And part of this is because the number theorists, for the most part, are only interested in number theory. So they know all kinds of fantastic things and do all kinds of things, but it sort of ends when you're leaving number theory and they lose interest in it. And so, for instance, even the residue fields in number theory, they're always perfect because you start with this LP. That's the residue field of the integers, which is perfect. And if you take a finite extension, then that will still perfect. So, but in algebraic geometry, a lot of people like to worry about those other things. Okay, so I think I have time to go through one fairly concrete example now. Tying this in with like what we learned in calculus class, smoothness. So let me do this. I think that's the stopping point. Okay, so this is an example. Suppose that F is an S-dimensional applying variety over an algebraically enclosed field K. Everything X. The primes contained by. Well, it's like that's dimensional. Well, we're working on that. If we already have that condition. Okay. Okay, so this what I'm saying here is that this ideal here. Okay, as we mentioned before, when the 12 points of X, the maximal ideals of KMX one I can be interpreted to the solutions with K to the N to the system of equations F1 up to Fn is equal to 0. Interpreted as the solutions A and Kn to the system of equations F1 J equals and is equal to 0. And so we identify the closed point X1, what is N1, Xn, what is An, which is a maximal ideal. Identify the maximal ideal is in the spectrum. So that maybe I should give this a name. Here, that's one. Maybe not. With A1 and N. So we can do that. I call maximal ideals of this form. And now for let's look at between phi and m. We can write that phi. We can expand it as fi to its p plus Li y. So maybe I'll write it like this, thinking with this, divided by square. Okay, so this is the constant term. Well, what you do is you can, for instance, you can expand this as a series in powers of well, with coefficients or monomials in these guys. And for instance, because there's a constant term, a linear term, and then higher order terms in terms of these guys, think of them as variables. And L sub I is just going to be the summation, A equals 1 to n. So A, Fi, L, J, evaluated at P, so in Xj minus Aj, like that. Okay, so now in any characteristic, this part works. Okay, now it has that, we notice that F on P is 0 for all pi, and by point B is an X. Okay, that's, you have to have this whole. Okay, so I guess I'm thinking the P is this guy. Okay, so the tangent space, this is another definition of reason. Or the tangent space of X on K, line space over K, and you see the X, but this is going to be the vanishing of all of these guys, these linear forms. So this is a linear subspace. Okay. Linear subspace, or if you will, a translation of the linear subspace. Maybe I should say translation. Translation by the point P. Okay, so I can compute that the dimension of PPX as a vector space is n minus the rank of the Jacobian matrix. X evaluated at P, and we get the dimension of PPX is bigger than or equal to X, and X is singular, and P, if and only the dimension of this vector space is equal to X. Okay, so and I will say, I guess, one more theorem. And in fact, actually, this is differential denominators also take this definition now. Now meaning since 1940 or something. Okay, so let's suppose that X is a variety over the perfect field K, where we know that's the good situation where smoothness and non-singularity coincide. Then the non-singular X is an open fence subset of X. Okay, and I'll make again the comment that algebraically closed implied perfect. Okay, so what this says is that over a perfect field, you really have the condition that it's a very special condition. Proper closed set with this. So, and in fact, although I didn't mention this, that for a variety, the set of regular point sets an open set, and it's also dense because of, say, if you take a domain and you take its quotient field, that's the localization at the zero ideal, which is the prime ideal, then that's a field, and the field is automatically regular. Okay, so I'll give one more example, and then I'll end at a good point.
But what makes it important is the fact that it's dense, right? Because it's always open, right?
Right, and that's like that. We have that theorem saying, okay, without this perfect field condition, it's an open subset, but it could be the empty set. That's in that example that we looked at. So that's the problem. Yeah, that's good. Bring out that one. Okay, so now we'll look at one concrete example. Okay, and instead of focusing on bad situations, let's focus on good situations. Okay, so this is maybe the simplest singular point you can have. And we'll take A to the algebraically closed field there's a 0, 1, characteristic P bigger than 3. In order to see taking derivatives here, there's going to be a problem here. If in purchasing 2 or 3, you're going to kill something off. Okay, so then you can give the program deal. And what is for your equation to y? And this is equal to 0. I guess I should say j y squared minus x cubed. That's y evaluate at a point is equal to 0, 0. If and only q itself is the origin, right? But except for at the origin, one of these guys is going to be non-zero. So what this tells you is that that is the only non-singular, in fact, the only non-smooth point. This is the only singular point. And so in this situation, K is algebraically closed, so being smooth over K and being non-singular are the same. Let's look at the tangent space in Q and X. This is going to be the vantage locus of this linear space. So linear, I mean, it's a translation of a line, which is contained in two-dimensional space. So this is equal to a line that A1 and 2 is not equal to 0. Or Q, I guess I should say Q here, A1, A2, and it's equal to all of A2. So P is equal to 0 here. Okay, so we have the picture here that I'll draw. So of course, I'm only drawing the real part of this. It looks something like this. This is the origin of course something bad happens. And if I take a point Q here, and this is the PQ of X. Right here. So this is just like what you do in calculus class, that you construct the tangent line to a point. But the difference here is that while you agree it's a bad situation, but at a singular point, you still have a tangent space. The whole thing there isn't a tangent line, as you know. But you can make the whole space a tangent space. Okay, so this is a good stopping point. But next time we'll start by finding what the resolution of singularities is, namely how you can make some small algebraic modifications in the space in order to maintain that there's an isomorphism over an open, dense open set, but still end up getting something which is not zero. Okay, so we'll stop here for today.
Thank you. Any questions here? Any questions online?
Okay, so I guess we'll stop here and we'll resume on the Thursday, I guess, 2 days from now at the same time.
No, I think it's Friday.
Friday, okay.
I asked Friday the 13th.
Friday the 3rd, okay, so that one's wrong. Okay, so
Yeah.
we'll meet on Friday.
Yes, so for those online, it will be transmitted in the same link, so hope to see you there. So goodbye. Stephen says, thank you, Dr. Cutkosky.
Oh, okay, you're welcome, Stephen. I was very happy to see you here.
Okay, see you then. Bye.
Okay, bye.
I'll stop the recording, so. Tá. Beleza, então na sexta-feira acho que vai ser lá no auditório, então. Não vai ser aqui. Tá. Obrigado. Tchau.